Oh, wait. Okay, thank you guys, and happy day 2 of the school. So the goal for lecture 2 for me is going to be to demonstrate that this asymptotic symmetry is equivalent to soft theorems for you one example. So let me write that down straight. This equivalence for soft theorems in the U1 example. And the point is going to be that basically, as we talked about last time with the IR triangle, that there's various iterations. And so you can pull through a lot of this derivation for any instance where you have a large gauge or a gauge symmetry interpretation of the asymptotic symmetries. But it's nice to stick to an abelian example where just like fewer indices in the gravity case. Also, you can decouple kind of the matter from the gauge theory part more readily. So this will be nice. And the point that we're going to be starting from in some sense is where we ended off last time, where we basically observed that there was this antipodal relation between the solution for the linear record gauge field strength that now we're going to try to push a lot further. So we saw that for this particular linear record solution, we had the following relation. We had basically at the pass limit of scri plus, so scri plus minus, the radial field strength was equal to the same antipodally related at the feature of scri minus plus. And now it's a pretty strong claim that Strominger and collaborators are making, I guess, or at least it's not obvious, it shouldn't be obvious, that we can essentially continue that for more general solutions in this particular linear record example we were looking for. So basically, it's some postulate that if you look at opposite sides of this Penrose diagram here, that various quantities such as the field strength or the metric are going to be related to each other, even though this is an infinite amount of time. And the subtlety is that basically, let me make that a little cleaner. Subtlety is infinity. The subtlety is, again, that basically it's an antipodal relation, which is not obvious from the bulk point of view. But I think Campiglia and Latta and others have tried to basically look at solutions to, say, the free wave equation for different spinning fields near spatial infinity and showed that there is indeed antipodal matching. So basically, a lot of what we're doing today is going to follow if you just start from the starting point. But it's worthwhile to spend a little bit of time trying to ask again what this quantity is, because in that situation, then at least so long as you can basically start from a physical interpretation of the fact that you're doing a gauge transformation on your fields, and you know why you want to be doing those gauge transformations, it makes a little bit more sense why you might have a condition relating in and out. Because right now it's just saying there's some basically boundary conditions of the field strength for physical solutions we're interested in that obey an antipodal matching condition. So let me go a little bit that direction before we go there, but let me just clarify one thing here. So this is going to be true for particular functions of z and z bar that themselves are antipodally related. We're going to cheat a little bit by basically using antipodally related coordinates on the celestial sphere. And this was all because we saw for the solution above that the order 1 over r squared Coulombic term was antipodally related, but had a non-trivial angle dependence for various boosted charges. So now it's natural to ask, what is this object? So what is this Q epsilon? And there's two references that I want to point out to you guys for those who want to study this in more detail. The first one is one with Prahar, I think Temple and Andy, basically asking the question of like proving this for the first time. And so it's very detailed. The only reason why I add another reference here is that the gauge choice is a little bit less convenient. So basically they're using some radial gauge versus this reference by Mina Himwich and Strominger is after a different thing. They're after a sub-leading version of the story, but they're using harmonic gauge. And so it's just slightly nicer to be using a gauge choice from the space-time point of view that's consistent with what we normally assume in like the momentum space expansions of the fields. So that's going to be nice. And so basically the next board is going to be unpacking a little bit what this object is from the point of view of this asymptotic symmetry story that I guess you're hearing more about in Yannick's talks. And so what we're going to basically see is we had our our Maxwell action written down before, and we found that the equations of motion were simply just this thing, where there's some matter current, and in particular last time we looked at the matter current being these constantly moving at different velocity charges. And the point is that here, this F mu nu is just our field strength. And also we have the fact that this current is conserved, and that's coming from the matter electron. Now, we would expect, of course, that there's a gauge symmetry in this story. And this gauge symmetry is just going to be shifting our field strength, since it's abelian, it's very simple, by a total derivative. And so one could ask the question of, okay, this is a gauge symmetry, and normally you don't think of gauge symmetries as physical symmetries, like you would normally distinguish basically something that's just a choice of coordinates, or in this case, a choice of, I guess, how we are writing this local field. And one would want to just say, okay, let's try to gauge fix away. So let's try to do that. Let's try to gauge fix. So again, going to the second reference, and it's a little bit more convenient, let's go to some harmonic gauge, where we're trying to impose the divergence of A is 0. And when you do so, then Maxwell's equations basically then are harmonic, right? So that's why it's called, I would call it that. But it's also called Lorentz gauge. And this would still allow us to have an epsilon of this form if we have the following restriction. We would want epsilon to be a harmonic function. And so when you have basically this type of condition, you can ask, what's the free data? So let's do a little bit of a notation aside. Let me maybe pick another color, because I secretly introduced a little bit of a funny notation that I want to make sure it doesn't confuse us later. And sometimes I'm going to need more terms of this expansion. But say I have an operator or a function of u, r, z, and z bar. And this is like the retarded Bondi time, so it's u is t minus r for those who want a reminder, the radial coordinate, and these projective stereographic coordinates in the celestial sphere. We would have the following expansion, r to the negative n, o, n, u, z, z bar. And sometimes we might need some logarithmic terms here. But I would use a different notation for the coefficients there. So anytime I write an operator with an upper n in parentheses, what I'm saying is extract basically the power of 1 over r out front. So right above there, I'm talking about the Coulomb field, which is the 1 over r squared part of the radial electric field. So my notation is there. And so if I do the same thing for, say, either trying to look at solutions of this gauge fixing condition, or of the of Maxwell's equations, or of this particular residual gauge fixing, then basically this turns into some differential equations relating u and r derivatives of this guys. And you can say, what free functions would I be able to specify to go order and order into the bulk? And so this is precisely the kind of simpler version of what Bondi, Vanderburg, Metzer, and Sachs were doing when they're trying to say that there's, first of all, some nice coordinate system that you heard Yannick set up last time. And then you want to basically say, what are the free functions of Scry that I can specify? And then I know the full solution in the bulk by basically integrating out those equations order by order in R. And so when I do the same thing for the scalar, what I find is that I would have basically E1, so the order 1 over R part of this scalar can be fairly specified. And I can use this to gauge fix away basically some component of my gauge field. So I'm basically going to use the free data in this harmonic scalar that is this gauge transformation of my gauge field to make the U component of my gauge field more suppressed in R because it's basically just shuffling around what I'm saying is my gauge fixing. But I still end up having basically only angle-dependent data that can shift this gauge field. So what I'm saying now is that I still have a residual, say, order R to the 0 part that's still a function of only z and z bar, no longer u anymore. And I claim that basically q epsilon generates this transformation. And I'm going to motivate it in a little bit, but I just want to point out a couple things about it. So normally, or I guess like when we use the word large gauge transformations, we mean something different than what you would sometimes see in the literature. So, and in Andy's literature, large gauge transformations means basically that it makes it out to infinity. So right, I'm saying that this survives as I take R to infinity, it's order R to the 0. And that would be distinct from, say, any gauge transformation that has compact support, for example. And the kind of claim of this story is that the gauge transformations that make it out to infinity shouldn't be thrown away or treated like they're unphysical, and we should take special care for them. And then basically now the point would be once you have these gauge transformations, you can go through this whole symplectic structure story and derive from Noether's theorem a charge for these guys. And I'm claiming that q epsilon is the charge for these. But I'm not going to go into the full derivation of it there. I'm just going to do a couple manipulations that will motivate that indeed we expect this guy, this q epsilon above, to generate the transformation corresponding to a gauge transformation that makes it out to null infinity on, for instance, my matter fields, but also on the gauge fields. So that's what I'm going to say. And so now let's proceed forward and basically play around with it. So one thing I can do, and nominally I want to also put the caveat that the things I'm going to start to do now, I don't necessarily need this interpretation. I really only need this antipodal matching of the field strength. But what I'm going to do is I'm going to start by looking at deleting large R behavior of the U component of my equations of motion. Okay, so basically I have that I will basically be just plugging in what we wrote right here, restricting to the U component, and then writing out all the terms. And so what I find is the following. I find that du of f ru2 plus dz fuz2 plus d z bar f uz bar of 0 plus e squared du 2 equals 0. And so what I want to point out, so basically I've moved some things to one side, and hopefully I have all of the signs right there, but you can call me out if I put a minus sign here.
Sorry.
Yeah, probably minus sign.
Sorry.
Yeah?
Can I just check?
Yeah.
So usually with the 0 you
Yeah.
expect the generator to be to codimension one, to be on a codimension one surface.
Yeah.
It's codimension two. Is there some?
So, but this is a gauge field. So it's not a global symmetry, and so even like in gravity or in gauge theory, I would expect the canonical charges to be codimension 2. So there's a 2 form. The 2 form is the field strength, and so the expression above there is how I'm basically taking the field strength star f, and then the only thing I'm doing that's different than the global one is smearing it with an angle-dependent function.
Yeah, sorry, yeah, think about. Yeah, thank you.
Okay, cool. Okay, so feel free to catch me if I accidentally put a sign here. But what I now have is the following statement. I can basically move things to one side or the other. And what I want to do is this guy was appearing in my charge. And I'm going to basically move everything to the right-hand side.
And these,
Yeah. Yeah.
DZ
Oh,
is the covariant
exactly.
derivative on the
Great, so call me out on these things. So my notation here, I take for granted a lot. This dz is a covariant derivative on the unit 2 sphere, where my metric gamma zz bar is 2 over 1 plus squared for this projective, these stereographic coordinates on the sphere. And then I also have introduced this notation where basically different orders in 1 over r can mix because there's various, say, either radial derivatives or whatnot that can appear here, depending on the components you're looking at. And so these are different orders in 1 over r, but together they appear in the same order in 1 over r in the equations of motion. Good. Okay, so now that I do that, I'm just plugging this in to the expression for the q's. And so I'd find that at future null infinity, and yeah, please keep the questions up. It's great to know when to slow down. And so I'm doing one more sleight of hand here that you guys will catch, hopefully. And we can talk about it a little bit. And that is that I've tried to use Stokes' theorem and ignored a second boundary term. So what I've done here is the following. Nominally, I've just plugged this in, moved everything here to the right-hand side, and then integrated in u. And so the integral in u should be the difference in 2 boundary terms. But the problem that I should be careful about is that basically what I have here is I've assumed that basically the contribution from I plus is 0. And so this would be fine if you try to assume something about there being no, say, massive charges. But if I had massive charges, I would have another contribution coming from them. And I would group that into this term here, which I'm going to call Q hard. Meanwhile, this term over here, I'm going to call Q soft. And the reason for that will be apparent in a moment. But just to keep in mind, this is coming from the matter fields. So basically, anything when I look at like the action of these guys on phase space, the symmetry transformations of matter fields are just going to be coming from these terms. But in particular, these are massless matter fields if they have any contribution at scry. So if on that Penrose diagram, I'm getting a non-trivial current for this gauge transformation that come from the matter fields, it's because I have to have massless charges leaving at null infinity. So I'm going to be a little bit careful there. But as a check to the claim that I made below, one can indeed see that this Q plus epsilon, say transforming a matter field, the only pairing should be from this second term here. And this should correspond to the phase rotation that you would expect. An infinitesimal version of that for the matter field. Right, so the point is that this matter field would have charge Q. And this is the current that you get from looking at a local version of varying the phase of the matter field like you would when you see how you covariantly couple a gauge field to matter. And so this is basically what I would expect for a charge that's generating now an angle-dependent version of this phase for a large gauge symmetry transformation. And so that's good. But we need to be careful a little bit. And this is where I'm going to give a little bit of a reading assignment for those who want to unpack it more. We have to be careful about the zero mode phase space. So basically, my homework assignment would be, you want to read section 2.6 of Strominger lectures. Because basically, there's a very subtle thing about what this is looking at. So basically, you could ask the question of, normally when I talk about like functions that are well-defined in null infinity, it would be great if they were square integrable. But there are tails associated with the memory effects. They're going to make AZ have a non-trivial kind of step function-like behavior. And so basically, at early and late times, this looks like, say, dz of some phi plus, some dz of phi minus. But one needs to have a little bit of care of how to talk about the symplectic pairing between these guys versus any finite energy thing in the middle. And so there's this factor of 1/2 that kind of plugged some of the derivations. And if anything, I would say the first papers by Strominger and Brahar and others, the insight was the antipodal matching. And then the technical thing that they had to be careful about was getting the right bracket on this phase space for the late and early U behavior. So I want to say that one should be a little bit careful here, and it's a fun story to look at, but it would take us a bit far afield.
And what is Q?
Sorry, Q here is the large gauge charge, and Q is the charge of the matter field, let's say.
And what is
E is the parameterization of this guy, so let me add that here.
E?
Is any function that I want. So E is appearing here.
Upstairs.
Where?
At JU.
Oh, E squared, this is basically the electric, we've stripped out the units of the electric charge in the story. So, sorry, so the charge would actually be, I guess, E times Q would be the, yeah.
May I ask another question?
Yeah.
Because in the upper left dashboard,
Yep.
Q plus epsilon is defined as an integral on the square plus minus.
Mhm.
And there is defined as an integral on the square plus.
Exactly. And so what I've done is I've made an assumption here that the contribution from Scri++ is 0. But I could just as well, if I had a massive charges, I would add a Scri++ contribution. And so, right, so basically what I'm saying is the difference between the Scri++ and the Scri plus minus contribution is this guy from this equation of motion. But that, strictly speaking, this guy would normally correspond to the charges for some massive charge particles. And if anything, would actually look exactly like the linear backward solutions we were looking at last time, the form of the radioelectric field strength for the configurations of the charges at like late times.
And this commutator is a quantum commutator?
Yes, so this should be acting in the phase space. And so nominally,
Shouldn't there be square root of -1?
I hopefully stripped out the phase in the right way, but I think there's also a phase rotation of Q, so hopefully I didn't get that wrong, but I could be copying it wrong from the notes. Sometimes they mix Poisson brackets in that, so I believe you if you say there's an I here. So homework, check if there's an I. Good. Okay. Yes.
Can we check this classically by computing Poisson brackets?
Yeah, so basically most of the derivation is coming from Poisson brackets, and so I think we're a bit glib with Poisson brackets versus commutation relations if there's any I's that are stray. But one thing to be careful about is still in the Poisson bracket story, you have to be careful about like going from the, like say the step function you expect for 2 gauge fields at different points on Scri, and then how you want to precisely handle the past and future limits. And so I think that like the first paper here, they're literally just kind of postulating some consistent brackets on some variables they're defining in terms of these early and late guys, that they're saying like the symplectic form should have like the standard form that you'd expect for the finite energy radiative guys, and then you strip off a part, which is the pairing between these. But there's a lot of notation that I would have to introduce to write that I didn't want to distract from, but it was subtle. And so I want to at least be honest about looking at that. Good. And we're going to see one kind of reason why the 1/2 comes in the derivation from the soft theorems, but there it's going to be kind of innocuous, and it's literally going to come from the fact that a very low energy radiation, the soft photon, sees both the incoming and the outgoing guys, where the matter part only couples to, say, the matter fields in the in or the out state separately. And so getting the full thing to work out consistently, that factor of 1/2 is actually a good thing. Good. Okay. So we would like to show the following. What we mean by our ward identity is out Q epsilon plus S minus S. And now if I were just doing the classical story, this would follow from the fact that I've said that the Q plus and the Q minus are the same because of the antipodal matching of the field strength. But now I want to actually just show it kind of, I guess, semi-classically by recognizing these as the operators that I get when I plug in this constraint equation, this U equation of motion in, and then I know how both of those guys act on the radiative phase space. So here we know that that's the matter charge and how it basically measures or changes the phase of the matter fields. And then I want to show that Q soft now is a soft photon, and that's going to be what I show in the next board. So in words, we know that QH plus minus measures the matter charges at square plus minus. So let's evaluate QS. Okay, and so now what I'm going to do is I'm going to start from the mode expansion of my fields at just some for a free field. So I'm basically looking at my quantum field operator, mu of x, in terms of the creation and annihilation operators that we know and love. Integral and so this in particular should be familiar, so if you have any confusion on the notation, stop me and we can go through it. But there's going to be a couple steps that are fun and maybe less familiar, because, yeah, I can say more. So, post-formation conjugate. Save space. And so what I've done right now is I'm just saying these alphas are just the two helicities. This A and then the A dagger would appear in the Hermitian conjugate term are going to be the ones that create or annihilate the single particle states. And this is just the standard plane wave, and these polarizations are familiar ones that you would have for, say, the two helicities. And omega q is my energy for this on-shell expansion. And so now what I want to point out is that for our gauge choice, we have that this field strength is just du az0 because the contribution from au is subleading. So there's no E0 component, so this is 0. And so basically, once I can extract az, then I will have this FEZ, which is the quantity and its complex conjugate appearing, or Hermitian conjugate appearing in Q plus there. So all I need to do now is basically try to evaluate the following. E0 So I want to take this guy and evaluate this AZ0 component so I can plug it into the QSoft. Okay, so now here's one fun thing that I actually really like about the story, and it's going to be how you connect position and momentum space more readily to each other. So if I want to go to large R, then I have a funny thing that happens with that plane wave. So I take fixed u, go out to large R, and I find that this e to the I q dot x that's appearing in this mode expansion simplifies kind of drastically. So first I'm going to write it out in terms of the part where it's like the u dependence. And then what I see, because I've said u, this difference, this retarded time as opposed to the normal time, is being held fixed when I go out to large R. Then I get this 1 minus cosine theta, where this theta is the angle between x hat and p hat, or q hat in this case. So the direction in which the momentum is going, and the direction in which I'm at null infinity, are this cosine theta, and r multiplies this factor of 1 minus cosine theta. So when I take large R, this is going to be rapidly oscillating, and I get a saddle point approximation where this all collapses into a phase in u and a overall prefactor. I'm just looking at the measure. And in particular, it's basically going to localize me so that the direction on the night sky in which I'm sitting at when I'm looking at what's happening is the same as the momentum. And that physically makes sense because if I'm like basically sitting very far away, anything that traveled to me had to have a momentum coming in my direction from wherever it started from. So that's the intuition behind it. But in practice, what I'm doing is basically looking at the fact that this is rapidly oscillating in R and trying to make sense of that saddle point. And so when I do that, this expression for this Anxiao field simplifies drastically, and I'm left with basically only one Fourier integral left over. And in particular, so I have basically one Fourier transform, but I wanted to do U integral. So what I'm going to do is I do the U integral, and it's going to basically give me a delta function here, and I'm just going to get a particular limit of omega instead. So the quantity I'm interested in, so this implies that integral du of f uz of 0 is -1 for 8 pi, some prefactors that aren't as relevant, limit as omega goes to 0, omega right there. Okay. So basically, I have, just from this manipulation of the saddle point approximation, that the integral of my field strength that I'm looking at, so this is basically the total integral, time integral of the amount of, say, the radiative radiation, that's 1 over r part of the field, coming out to us at infinity, is just the coefficient of omega times this insertion of a soft photon creation or annihilation operator. But beautifully, Weinberg tells us that this has a very universal form. So Weinberg tells us that these insertions have a universal form. And so what Weinberg...
If we
Yeah.
integrate over omega, why there is omega in the numerator? If we integrate e to the minus omega u,
good. So that's because I didn't just do AZ here, I did FUZ. Yeah, good. So at least it's nice when you don't have to erase the board, so it's like FUZ, good. Awesome. So the omega comes from that, and then one should be careful, right, that I'm saying, like if this thing weren't singular, so if I didn't know that there's a Weinberg pole here, you might say, oh, this should just be 0, but the point is that this is non-zero. And so what Weinberg tells us is that if I have a scattering process, and then I add an extra soft photon, it's going to attach, it could attach to something else in the diagram, but whenever it attaches to one of these legs, if this is momentum q and omega q is going soft, then the propagator here is going to give me a pole that's going to give me a 1 over omega in this contribution. And so in particular, I find that I have out a plus of q s in. So this is the out state with an extra soft photon, is some sum over in minus out, out minus in, of some charges plus something that's order omega q to the 0 at tree level. And so basically what I'm saying here is that this is supposed to be the leading behavior as I'm taking omega q small, and this soft theorem itself is going to be used universal even beyond tree level. And then the subleading terms can get corrections at tree level, or beyond tree level. So this is Weinberg's soft theorem. And now we can get to our punchline. Which is the following. So I'm going to plug in soft theorem. I find the following. I find the out is the following form, where qk is the charge of the different states, and I have a sign weighting in versus out for my given S matrix. And then all I would basically need to do is evaluate the following. Basically, right now I've showed how to evaluate the Q soft, and then I just need to compare that to Q hard. So the way that the proof works is that I just take the same thing that I've done before here at scribe plus. I do the same thing at scribe minus. And I've just shown you how to evaluate this part of it.
Is it supposed to act on vacuum or?
In, yeah. Thank you. Good. So basically what I've done is I've showed you how to evaluate this guy. This is the Q soft. Q hard actually should be simpler because Q hard is just going to measure the phases for the particles. And then just double check that these things make sense. The point that I want to mention is that if JU is going to only basically click when there's a particle that's sitting somewhere at scry. So basically say there's a charge that's moving out and makes it to scry. So maybe it's massless, so it's moving out. JU is going to basically only be non-zero where that particle happens to have charge and leave scry. And so we expect basically some sort of delta function or contact term wherever those hard particles happen to be that are charged. Now, over here, we saw from the soft theorem that this has a non-trivial angular dependence. So basically, I can kind of non-locally on the celestial sphere see where there have been charged particles at other points in the celestial sphere. But that's all consistent because if you see these equations above, there's supposed to be a derivative hitting f. And so in particular, right, if I have, just as an aside, so it's worth clarifying, if I had a z bar of 1 over z is 2 pi, like, I was saying. Right, I'm going to my convention. So basically, depending on my convention here, there's a delta function coming from this guy. And so roughly speaking, what I want to say is that I am picking up what's consistent with those equations above, because basically, so depending on the normalization, this is just proportional. What I have is everything's consistent because basically this guy is measuring what basically the field strength is away from other charges, but it's related by equations of motion to something that I've matched. And so what I would like is that basically the divergence of that field strength term is equal to the sources, which is exactly what I get. And so that's roughly how this equation should be read. It's that here I have some insertions of this soft photon. They will measure where charges were either on the in or out celestial spheres. And here is where the charges actually are. But in the soft charge, I have some derivatives hitting either the smearing function if I integrate by parts or this guy itself. And it's consistent on both sides. So that's good. So then, given that, we've kind of finally proven what we wanted to. So indeed, we have basically out q epsilon is s minus s q minus epsilon in equals 0, which is the goal. But I want to say one more thing. If we define the following object, which is basically just the q soft for a very particular choice of epsilon, then we basically get something proportional to this integral that I wrote above here. Right, so basically what I'm saying is that q soft isn't this guy. Q soft was a smearing of this guy. And so depending on whether I want to do this trick that I was saying above to see that this does satisfy the word identity, that basically plugging in f is consistent with the equations of motion because derivatives of f give you delta functions where the other charges are. That's good. I could just as well try to basically pick a particular epsilon so that in the expression is written there where the derivative is hitting epsilon, I get a contact term, which then just leaves me the u integral over f not smeared on the sphere. This object is going to obey this very nice thing. It's going to obey that insertions within an S matrix element look as follows. And so all I'm saying is basically literally evaluating this first line here, but then trying to be sneaky about it and say, what if I could say that each of my in and out states correspond to some operators, and I'm labeling them by some label I'm not talking about, which is in this 1 or n subscript, and also the points in the celestial sphere. Then this guy looks like I might have a Kac-Moody symmetry. So it almost looks like this asymptotic symmetry story of this large U1 gauge charge gives me a 2D Kac-Moody symmetry, an abelian in this case, of my S matrix. And so that's going to be kind of the big question or the cool thing about it. So let me then go back to the intro. Let me pull this down. And say what we've shown and where it leads us. So let me, I guess, just erase everything here. So for today, this was our goal. And so indeed, our takeaways are the following. First, we saw that the soft theorem equals this ASG word identity for this UN example. The second thing is that we see that basically these word identities correspond to infinite dimensional angle-dependent enhancements. Of the symmetries we might expect otherwise, which is, say, global charge conservation. And then on top of that, these guys look like they're 2D currents. And so for tomorrow, or next time, we're going to basically push that further. So the goal for next time is that we're going to start to reorganize scattering. To make these symmetries manifest. And I think that puts me close to time with the questions. So that's what I wanted to show. And let's have questions or, yeah. Yeah.
If this derivation is correct in the loop level,
In which paper?
loop level, Weinberg.
So the derivation of Weinberg's soft theorem is in this 1965 paper. Or some in the 60s, and then the derivations of like the word identity is in this paper.
He's asking if the soft theorem holds at loop level.
Oh. It does hold at loop level. I'm trying to think if it's if the arguments in the Weinberg paper are make that manifest. I would assume. I think they do. Yeah. So. Good. Yeah.
Why, so at some point you write down the limit of some error to 0?
Yes.
Why don't we just say that this is identical 0? You said something about poles.
Yeah, because basically this function A has a pole coming from this 1 over q here. So the propagator is giving us.
The Weinberg soft.
Exactly. So that's what I'm saying. So it is exactly Weinberg's soft theorem. Yeah.
Where you write J is equal to Q soft.
Yes.
There.
All right. Sorry, look where you're pointing. Okay.
Yes. So
Yes.
why do you write that the current is equal to Q soft?
So I just chose, I put a subtle like definition symbol. So what I'm saying is that I want to basically give you an object that I might say is interesting later. And so roughly speaking, the question of, you can split it into two things. On the one hand, you're saying, I have this large gauge symmetry transformation, and so I want to say there's a conservation law for like any function on the celestial sphere. And then I get that, and there's now, instead of one global charge, there's basically however you want to decompose scalars on a sphere, that many charges. But in particular, what was interesting is to try to treat it as if let's look at a very particular function, so look at the holomorphic ones. And in that situation, I'm just saying that that derivation for the asymptotic symmetry story for any epsilon further implies that there's this Kac-Moody symmetry. So that's the aim of doing that.
You're saying that if you restrict yourself to the holomorphic one,
Yeah.
you have this.
Exactly. So the one implies the other. And then also in particular, there's kind of this nice shadow relation between the two helicity soft theorems that's letting this go through with just an extra factor of 2 out here. But in higher D, you have to be a little bit more careful. Good. Any further questions? Yes.
So I guess you also have to assume that there's no distributional support around omega equals 0 in A.
One would need to be careful. I think that if there was, strictly speaking, a contact term, it might still vanish from the, like, to what extent does, like, 0 times delta of 0, like what you're mirroring that against. So one needs to take care there. But in principle, I think this should still just be the memory modes and not any Goldstone-like mode. I think we'd want to kill it. One thing I do want to point out, and it's kind of inspired by this recent paper, or not inspired by, but connecting to nicely the recent paper by Richard, is that, right, the saddle point approximation is really what's letting you kind of view this connection between the things that you're doing in position space when you're looking at, like, moving around on this asymptotic phase space, and scattering amplitudes as you know it. And so in particular, if we're inserting AZ on an outstate and saying that it just creates or adds an extra soft photon, like, instead of doing LSC, we're roughly doing an extrapolate dictionary. So just want to point that out. Any further questions?
So what is the expansion between yachts?
Say again?
What is the expansion between yachts?
I don't know. I somehow I didn't understand the expansion between.
Yeah, so for Katsuri you need yacht.
Yacht.
Yacht of 0.
Sorry, I don't know if I know what yacht is.
JJ.
JJ. Oh, sorry. So for this guy, this is okay. Sorry. I guess I'm going a bit jumping to the Katsuri story. There's 2 ways to make it a non-zero level. One of them is basically, because this is abelian, it's going to be 0. So I can either go non-abelian and then I have, say, 0 level, but I have at least a non-trivial algebra for the JJs. And then, or I can go to the Goldstone mode symplectic partner and look at loop level effects and argue for another J where there's an off-diagonal level. So, so the first thing, this is just abelian, and then the second thing is it's also 0 level. So, as written right now. So 2 kind of things that are less.
So in this case just regular.
Yeah. So this is just abelian, but there is a non-abelian version of it that also is 0 level that I could just do the same thing, and then I'd have to be a little bit cleverer to try to put a level in there to make it more like 2D Katsuri standard stuff.